Hello and welcome to our latest office hours. My name is John Kowalski. I'm part of the marketing team here at BYK-Gardner and like to welcome you. Today we're talking dispersion and media milling. This is actually part two of a session we ran a couple weeks ago on dispersion. Today the part's media milling. If you missed the first part, take a look in the chat. I put a link to our YouTube page. You can check it out there, as well as all of our other web seminar archives. There's a tour of our Wallingford lab, lots of other good things. So check it out. Couple notes before we get into the presentation. We are recording this. Immediately following the presentation, you'll receive an automated link with this presentation. Feel free to watch it later, share it with colleagues, whatever you like. Also, this is an office hours format. Usually we have these on Wednesdays, but this is a special case here to accommodate our speaker. And it's usually a shortened presentation with a little more time allotted for questions discussion afterwards. So we'll get to that. If we don't get to answer your question, we will follow up with you directly. We'll record those and make sure you get those questions answered. Our presenter today is our dispersion expert, Mr. Andreas Stummer. He is our director of dispersion for BYK-Gardner and VMA-Getzmann for the US and Canada. So Andy, welcome. Glad you're here.
Well, thank you, John. Welcome back, everybody. Some of you may have joined us a couple of weeks ago when we did the first part of our dispersion office hours. And as you know, dispersing is always two parts. So we have our pre-dispersion process, and then we have our milling process. And today we'll talk about the milling part. But before we get into that, we're going to do a quick introduction into the company, the relationship VMA to BYK. Then we're going to do a quick overview, just a couple of slides on pre-dispersing, and then we're going to dive right into the milling part. We have a few slides on different types of equipment, milling, different types of milling attachments, milling systems. We show you some slides on production equipment, talk a little bit about quality control because that always comes up. And then the lab capabilities that we offer, as John had mentioned, we have a really beautiful lab in Connecticut with our sister company, BYK USA, where we can do trials for customers, and you can join us to see how the equipment works and how it would benefit your application. So with that, just give you a quick overview. So VMA-Getzmann is the company that actually manufactures the disper mats. They were founded in 1972, so over 50 years ago in Germany by Hermann Getzmann. You see a picture right there, the beautiful couple. And he's still involved in the business. He still comes in once a week to make sure that, you know, the team still follows his design philosophy. And we'll talk a little bit about that. The company is actually run by his two sons, Christian and Martin Getzmann. They have about 100 employees. They're still family owned. And BYK-Gardner, or BYK, has had an exclusive distributorship with VMA-Getzmann since 1988. The old CEO of BYK brought the units over to the US. They had it at BYK USA in their labs. They brought customers in to show them the labs and how everything functions. And then customers came back and said, wow, we really like the disper mat. It looked really neat. And that was the reason why we brought them on board and offer that solution here in the US and Canada. Since 1988 as part of BYK-Gardner or BYK Instruments, as some of you are familiar with. And VMA is known to make really good quality dispersers, dissolvers, bead mills, basket mills for lab, as well as pilot and also production. We actually started offering production capability here in the US about 5 years ago. And it's a really good mover for us, and customers are very satisfied with the performance. So here's kind of a slide that shows you the layout of the company in Germany. So they're located about 30 miles east of Cologne, so kind of in the center of Germany. And the building in the middle is actually, there's a new addition in the back for more workspace. And on top, the top level has a new design center. So we have actually 8 engineers now. All they do is design different systems. 40% of everything that VMA makes is actually custom. So there's a lot of new end markets, as we call them, for example, batteries or fuel cell. So we try to be really flexible to these customer requirements and accommodating them. Again, trying to provide solutions from everything from small volumes all the way up to really larger production runs. And then we have these lab spaces available in Germany as well as at BYK USA here, where we have some of these machines where we can show you how they actually work. So the reason we are dispersing and milling is pretty simple. We want to have a better product, right? And some of these, you can read them here, these attributes. We improve our wetting. We really, when we talk about dispersing and milling, we don't want to destroy our product or pigment particles or parts. We want to just really break up these invisible forces. They're called Van der Waals forces that are holding our particles together. These aggregates, primary particles turn into aggregates, these invisible, almost electromagnetic forces. And then the larger clusters, we call them agglomerates. And all we want to do is when we are dispersing and milling, we want to really just break up these binding forces. That's all we want to do. We don't want to really destroy any particles. We just really want to break up these invisible binding forces and reduce them back to the primary particle size. That's the idea when we are milling. So that will then lead us to a much better looking product. So that gives us stronger color, better gloss, and overall improved appearance. Pigment efficiency is going to be improved dramatically. So it's going to help you save money because you're going to need less of the pigment in your formula, because if you disperse it properly, you're going to get more mileage out of it. So that's a huge cost savings, especially when you're talking coatings. Pigments are the most expensive component that goes into these formulas. So we always want to help customers minimize the amount of pigment that goes into these formulations by offering a really good milling solution. And that will also give us better product consistency. And then, of course, formulation improvements. And then finally, we want to achieve a really consistent particle size distribution. And that should also help us when we go from lab all the way to pilot to production, that we have really good upscale results. So we want to really do a good job there in the lab to start out with, to make sure that our production runs are satisfactory and we have a really good quality product we can sell to our customers. So there are some issues if we don't do a good job dispersing of our product. So we're going to have color shifts, poor stability of our product, flocculation of pigment. So that's something that can be solved also with the right additive that BYK USA offers. Sagging, leveling, or settling, or reduced gloss or haze levels are some of the issues that come up. Separation, if we don't do a good job dispersing and milling. So here's a great example. You can see on this grind gauge drawdown, we see on the left side, we see a product that was pre-dispersed with a dissolver for about 30 minutes. Probably started out about 100 microns of particle size, and then we were gradually reducing these larger agglomerates down to the aggregate level. But as you can see, it doesn't really look all that good. But then when we continued milling, we achieved a much more consistent product, better looking product. And that was the result of further reducing our particles from the aggregate level down to the primary particle size. So that's the difference between just using a dissolver versus using a milling system. But we always want to start out pre-dispersing with the dissolver first. It's an important critical step before we actually start to mill our materials. So this is really critical. is that the stability of our products, so pigments require really strong color fastness to reduce fading over time. That's important, exterior products. So brightness, the brighter the product, usually we get the best color. Most products, obviously, the smaller my pigment particle, the further I mill it down, the better it will be my end result, better transparency color. And then, as we discussed before, you're going to use less pigment, which is going to be a huge cost savings. And then we want to watch out for viscosity. Viscosity usually is an important factor when we're dispersing and milling. We want the material to be flowable and allowing us to really put the material, pump it through the medium mills that will allow us to mill more efficiently. It's very difficult to mill pastes because they get stuck inside of our mill, or we can't pump them through a basket mill, for example. But if also our viscosity is too low, then it's very difficult to put in enough energy to really break up these aggregates and turn them into primary particle size. So we want to shoot for about 2,000 to 5,000 centipoise. Doesn't mean we can't still mill when we're lower, but we may need a little bit more time. And then if we go above 5,000, then it's still fine, but it may be a little bit more challenging if we have some issues with flow with certain milling attachments. So we want to remember here that we really don't want to destroy our pigment particles or primary particles. We really want to go and just break up these binding forces, and these agglomerates and aggregates are basically reduced back to the primary particle size. And shear forces is really what is responsible for that mechanical separation, of these particles. And then the additives are important that we can keep them back in a suspended state. Here's just a quick slide showing the different particle sizes of different pigments. Always interesting to kind of show what we're trying to disperse. And then, as I mentioned earlier, just a quick overview. So here is what's critical is the larger clusters. As you can see on the bottom right there, the circle, these building blocks, these large blocks, we call them agglomerates. And these agglomerates we want to reduce down to the aggregate size of smaller blocks. And that's how we go about doing that, is with the dissolver. So we use a blade with teeth. Some people call it impeller blade, cow's blade. And then from the aggregate level down to the primary particle level, we would do the milling part, which is what we talk about today. So that's important to understand, is that it's always a two-step process. So we have first to agglomerate and then to mill down to the primary particle size. So this slide kind of lays it out. So here you can see the dissolver disc. We are wetting our particles, break up these agglomerates, and then when we reach here is a good figure to keep in mind. The appropriate size is between 10 to 30 microns is kind of the threshold, and lower than we start to milling. Anything less than 10 microns, we really can't put enough energy in with the dissolver blade. We really need to start the milling process. Then here you can see a rotor. And then finally, once we're done milling, then we need to stabilize our particles with the right additive solution. So this kind of lays it out. So we start out with the dissolver. And then once we reach about 10 microns, as you can see here, usually between 10 to 30, depends on the formula, that's when we move over to the bead milling. And that allows us then to go really small. We have some customers that want to go all the way down sub 100 nanometers. And with a nano kit, and for example, a horizontal medium mill, this is really no problem. And this allows us to get there. Okay. So then here, again, this is the two-step process. So pre-dispersing, keep in mind, we talked about that last time, is the impeller speed, 18 to 25 meters per second. That's optimum. And when we are milling or dispersing, we slow down our rotor or milling disc speed. We can do that between 10 to 16 meters per second, and which should give us really good milling results. And we have 3 different types of milling systems. So we have vertical bead mill. We'll talk about that. We'll talk about the basket mill, which is getting very popular because of the ease of use and just low maintenance compared to the horizontal bead mills, which we also offer. But there is, obviously a need for milling with a horizontal bead mill, and that would be particle size. So a basket mill will probably allow you to go down to about 500 nanometers limit, and then anything smaller, you probably need to use a horizontal medium mill. The vertical bead mills, the APS, are excellent for the lab, but they're not really scalable, and we'll also talk about that. So just quickly remember, dispersing the blade diameter, we always shoot for about 1/3 of our vessel diameter should be the diameter of our blade. And then depending on, the viscosity, you can make some adjustments, but try to start out with about 1/3 of the diameter. And you can find this table on our website. So if you have a 1-liter vessel, for example, then you can see here, you have a range from 70 millimeters all the way down to 30 millimeters, depending on your viscosity. So the lower my viscosity is, the smaller my blade. If I have very thick viscosities, I want to increase the blade diameter to get the product moving. Otherwise, you'll have a blade sitting in the middle of your container spinning, and then all the product just will kind of sit around it and not do anything. So you want to kind of dial that in. That was important. And then this formula is true for pre-dispersing as well as milling. Remember, 18 to 25 meters per second and 10 to 16 when we are milling. So we basically have the RPMs multiplied by pi, and then times the diameter of our milling disc or impeller. And then if we want to get meters per second, we would divide everything by 60. And that means also that we would have to express the diameter of our milling disc in meters. So if it's a 50 millimeter blade, then you would have to multiply by 0.05 as in meters, and then divide everything by 60, and that will give you meters per second. And that's the formula that you should be using. That we briefly talked about the donut. So the donut is important because it's a visual cue that allows us to kind of gauge, are we pre-dispersing properly, and are we optimizing all the parameters, our tip speed, the energy we're putting in, and so on. And then if everything is done correctly, we should be able to actually see that beautiful donut form. And that means now we're pre-dispersing and we're in the right window. So the pre-dispersion time usually takes about, depending on the volume, but also the formula, I would say we don't pre-disperse much longer than about 30 minutes. And then we would move over to milling. So to optimize our pre-dispersion results, we obviously 15 to 30 minutes. We want to look at the donut effect, tip speed 18 to 25, the correct diameter of our milling disc to container ratio, and then the right impeller disc. There's many different types or shapes out there, depending on what you're trying to do. So some customers design their own. So just make sure that you use the correct disc. Volume, about 50% filling ratio in our container. Pigment filler concentration, so that's formula related. We try to keep the temperature usually as low as possible, because when we are dispersing, we are putting in a lot of energy. So that basically means we have to use double wall containers for cooling, and that will allow us then to maintain a workable temperature, especially when you're dealing with solvents. You're going to put in a lot of energy when you're milling, and there you really want to have a good chilling system to control it and stay within a good temperature range for your formula. We talked about the additives that help you stabilize everything, give you better performance, and then particle size is critical. Anything, so 10 microns is kind of the threshold, and anything that we want to go smaller, that's when we move over to the milling part. So when we are milling, compared to just using a blades, because we have customers sometimes they say, hey, can I achieve a good result with just a dissolver? Depends on what you consider a good result. But the problem is with the dissolver, we can only put in a certain amount of energy. That's why 10 microns is kind of the threshold how low we can go with the particle size. So with the bead mill, we can put in a lot more energy with our media, allowing us to really go and further deagglomerate down to nano-sized particles and really break down the particles to the primary particle size, which gives us the critical product characteristics that we're looking for, which we already talked about before. But don't forget, we always want to pre-disperse first to make sure we're wetting everything and we properly, deagglomerating, because what happens is if you don't do it, and let's say you start out with 100 microns and you go into a bead mill and you have a screen in there or a dynamic gap, if the particles are too big, that means you could clog your screen or your dynamic gap. Now you no longer have flow of your material. And often we see that the reason was the pre-dispersion step wasn't sufficient, or the particles are still too big. So we want to make sure that you measure that maybe with a grind gauge before you start milling to know exactly, hey, this is now a good time. Now we can start the milling process with the bead mill. So when we talk about milling, we always talk about, that we have media in there. So basically, if you look at that slide right here, inside of a milling chamber, you have a certain volume of beads, right? And these beads will get thrown around with tremendous force, depending how fast you run your rotor or your milling disc. So we talked earlier, 10 to 16 meters per second. So that's pretty quick. And as these beads collide towards each other, the shear that's being, the force that's being built up, the shear is actually pushing away the pigment particles or these aggregates, and that shearing motion or force will actually cause the breakup of the binding forces, continually reducing the particle size. So it's not that we're actually crushing our pigment particle, we're actually really just trying to break up the binding forces even when we are milling. So the probability of a particle actually getting crushed is very small. I always look at it or think of it this way. When you were a little kid and you were sitting in the bathtub and your mom gave you a rubber duck and you were trying to catch the rubber duck in the water and you were pushing your hands together, what happens? The rubber duck pushes away and it was very difficult to actually get the rubber duck, catch it in between your hands. That's kind of like exactly the same thing what's happening inside of a bead mill. So, but obviously there's a lot more force, and that force causes the particles to the binding forces to break up and reduce the particle size. So this is actually what's happening in a mill. So the probability of a particle getting crushed by two beads, it exists. Obviously, we have a lot of beads in there, so they're always drifting towards each other at very, very high velocities. And it could happen that so that one, an aggregate would just happen to be right in between, float in between two beads as they're coming together, and it would just, crush it. So that does happen, but it's very improbable. And it's more likely that the binding forces are broken up. So that's really what's happening inside of the bead mill. And we're using the shear forces to do that. So it's deagglomeration, getting the aggregates down to the primary particle size, wetting, and then again stabilizing with the right additive to make sure that they can stay in a suspended state. So what's really important also when we talk about milling is the different types of media. So we always recommend that you use zirconia media, ceramic. There's different types, but they give you much better performance than glass, for example. Glass is weak, it shards very easily, it doesn't have a high specific gravity, as you can see right here. So means you would have to put in a lot more force to kind of get the same, kinetic energy into our process than when I use higher weight beads. The glass breaks, unfortunately. You can see that customers that are using glass beads, they tend up breaking them over time, and you end up with shards in the mill base. They wear much quicker. You can see the hardness of 400 versus almost 1200. So the zirconia bead is about 3 times harder, and on the Wicker hardness scale. So basically, these are things that you should remember. And also, depending on what you're trying to do, but steel beads are not great either, especially when you talk coatings or new end-use markets where color stability is critical. Because by using steel, you're actually causing the metal of the bead to wear over time. And that would actually, also the milling component, the disc, the rotor, all that. And that metal wear would actually bleed into your mill base. So we have actually seen that milling over time will discolor your product if you're using stainless steel components. And then you can turn, let's say, a beautiful white slurry into a really nice looking gray slurry. So the answer there is don't use steel, use zirconium products, zirconium milling chamber, milling disc, and zirconia beads for protecting your material. And obviously some end-use markets, new end-use markets like battery, for example, you cannot use any metal anyways because it would interfere with the performance of your product. But always try to stay with higher quality beads and don't use glass or steel or anything like that. And then there's many different bead suppliers out there. Some are more expensive than others. Usually what we find is the more expensive they are, the better the quality. And you can see that when you look under the microscope, the more expensive media is usually perfectly spherical. And that is also important because if they are not perfectly spherical, then they will wear differently. And then you're also going to have inconsistent milling performance. Then you're going to have more fines. You're going to have to screen more often. So always try to spend a little bit more on beads. You will have a better performance of the material. So here, again, this is a great slide showing kind of the influence of the bead weight. Think of it this way: if you have a wooden board and you have a nail, and you're trying to drive that nail into the board, and you use a small hammer, like a goldsmith. It will take you many, many blows to really drive the nail into the board. Or you may never be able to get it into the board if the wood is too hard, when the nails are big. So it's very difficult to get that accomplished. So as I'm increasing, the weight of my hammer, then it'll be easier to drive that nail into the board. I'll need less impacts. Obviously, a super hammer, as you can see, 1 impact versus 100 impacts on a small hammer. So that's kind of like zirconia beads, glass beads. So there is a difference, right? This is all related to the specific gravity and weight, but that kind of explains it a little bit in other terms that may make more sense to you why that is important. So here is the formula for kinetic energy, how to calculate that if you want to write that down. So weight of the beads times the square of the peripheral speed or tip speed of our rotor divided by 2. That will be the energy or kinetic energy of the beads during the milling process. I really like this slide because it shows actually what is happening in the mill as we are milling. So on the left, you can see the bigger particle. It's kind of like an aggregate. And then as these beads collide, it gets pushed away in those corners right there. That's where that shearing, that shear force is actually getting built up. And then that particle gets pushed away, and that will reduce the particle size. So that's actually what we're showing here. So the more often you do it, the further you reduce the particle size. So sometimes there's a question, how long does it take to mill down, let's say, from 10 microns down to 2 microns? So that really depends on what you're milling. But we have seen some instances where we're milling in like less than an hour. we get very good results. We know that we've proven it. People that use 3-roll mills for some coatings or ink applications, they have to mill sometimes for days. We had one customers that had 3 different products, and they came to us and they were looking at a basket mill, and we were discussing the application. They told us that they use a 3-roll mill in production, and they sometimes need 2 days for a yellow to get down to the correct particle size. So they didn't really know what to expect when they came to our lab. And then we took the TML1, which is our basket mill, and we were milling it, and we were done in 1 hour and 45 minutes. So just to give an example how efficient we can mill when we optimize all the right parameters. So talking about the parameters, so particle size after pre-dispersion, we already talked about that, 10 to 30 microns. Bead size, weight, the bead type, ceramic, very important. The amount of beads, that really depends on the type of milling system you have, basket mill, horizontal bead mill, or vertical bead mill. The bead shape, are they perfectly round, as I just talked about? The tip speed, 10 to 16 meters per second to optimize that window. Temperature, very critical. You must have cooling, especially when you're milling. The amount of energy we're putting in, the number of passes through our milling chamber, the overall milling time, viscosity, make sure that it's flowable. Again, 2 to 5,000 centipoise is kind of a sweet spot, especially when we're using a basket mill. That always works out really, really well from a flow point of view, good rheology and viscosity. So we make sure that it goes through the milling basket really nice. Milling tool diameter, same principle as a impeller disc or a cowl's blade. And then the type of material, again, stainless steel, even though effective, it'll give you issues with coloration. So if you're only running black or dark material, it's not a big problem. But when you're running whites, then absolutely you must use zirconia because it'll will not discolor your material. So, and then obviously the different designs, vertical, horizontal, or the basket mill. We'll talk about that in a moment here. But early on, I mentioned something about the design philosophy of Mr. Getzmann. And you can see here what we mean by that is the modularity. So his idea was he wanted to create a solution for a customer that buys a dissolver, a Dispermat, which is actually the dissolver, which is the critical part, the first part in our, dispersion process for pre-dispersing. And then he wanted to give the customer the opportunity to also mill with the same machine. So he developed the basket mill. That's kind of like a quick change system, how it can be, attached in less than 1 minute with this bayonet style clamping ring. You remove it and you turn this assembly 180 degrees. And now you're able to just pop on a basket mill. And then you're off with the same machine you're milling. So basically you need less desk space. You can mill on the same machine that you did your pre-dispersion. And that is a huge advantage. You don't have to learn, a new control panel. Everything can be done on the same machine. You could also add an APS, which is our vertical bead mill. This is great for laboratory applications, quick color changes. It's excellent, but it's just not scalable. And then you could also add a rotor stator. Some people like a vacuum system if they have foaming issues, or some people work with adhesives. They don't want any air. So we can disperse on the vacuum. Milling on the vacuum is also possible. That takes the air out of our formula. And if you think about it, like the air entrapped in a mill base, these are tiny air bubbles. And look at it this way, they could be like almost like little air mattresses, and they buffer the blow of the beads when we are milling. And by removing them, I have more energy that I can apply to my pigment or my particle. And that basically gives me improved milling efficiency. So some people really like to mill under vacuum. Not all formulas have that problem, obviously. We see it often with waterborne materials where there could be a foaming issue, some oil-based products, but there's also defoamers on the market. Very small percentage, like maybe 1% of a defoamer that goes into a formula that can help with that. But we do have customers that really want to mill under vacuum, so that CDS system can do that. And then we have wall scraping units for very thick and pasty materials. It's the ASC unit that you can see on the bottom right there. So that modularity is important. So here you can see a close-up of a Dispermat, that beautiful bayonet style clamping system. You remove that ring, turn that assembly, the shaft assembly 180 degrees. It comes right out, and then you just pop on the different attachment that you want to use for your application. Small laboratory dispersers can go up to 20,000 RPMs. The larger the machines go, the smaller the maximum RPMs, because my blade diameter or my milling disc diameter is larger, allowing me to still get to the right tip speed. And then also some customers prefer explosion-proof designs. If they're running, solvent-based materials, we have that. We also have for our premium model that you can see right there, the software options for downloading or storing the data, giving batches, a name, or storing it by product ID. And we have that available for lab pilot as well as manufacturing. So the modularity means I can have one disperser, can function as a homogenizer, emulsifier, and disperser. That allows me then to also mill. So with that, let's talk a little bit more in depth about the different milling systems. So we have a basket mill. A lot of customers are moving over to a basket mill concept because it's just a really nice way of milling. I have to say, if you have good flow, and your particle size requirement is above 500 nanometers, there is no reason why you should not be using a basket mill. You will thank me many times if you look at that, because you will save a lot of money, time, aggravation from a cleaning perspective, maintenance hassle. There is no seals or O-rings or anything like that. There's not a lot of wear. The only real wear in a basket mill would be your milling disc. It's relatively inexpensive to replace, or your screen on the bottom. There's different designs out there. Our design is such that we purposely don't have a screen or opening on the side of our basket, because we want to make sure that we're cooling the mill base all around. And also, this is where you would be milling, is right in the center right there of our basket, where all the beads are located. And if we have a screen on the side, we can, number one, we can't really cool it properly. But a much bigger problem is the wear on the screen, because this is where all the beads will impact. The screen is on the side. So you would see very high wear of the basket mill if you have a design, if you have a design like that where the screen is on the side. So that's why we have a screen on the bottom, and then right below the screen outside is actually a cowls blade that will allow you to basically remove the mill base from the basket, pump it back around to the top, where then we can get sucked back in to the basket with that vortex wheel that sits on top of the milling disc, and we have a very good flow in and out of the basket, giving us really excellent milling performance, not only from a lab scale, but also from a production scale. And this is where this can be really powerful because you don't have a lot of downtime and cleaning time on the equipment, much better than horizontal mill or three-roll mill. Three-roll mills are also dangerous, and they take a long time. So we have a lot of customers that are moving away from the three-roll mills now to our basket mill design. So that's just a picture of a basket mill. That screw right there, that nut, you remove it to fill in the beads, and then you can kind of see there's a vortex wheel that sits right below that entrance, and that would actually, create a vortex and suck the mill base into the basket for optimal movement of the material in and out of the basket. Okay, so depending on small volume, large volume, we get extremely good upscale ratio, very easy to clean. Our design, as I already mentioned, that very simple, easy to handle. Cooling is excellent. And then we can also offer a nano kit that allows us to really go down to about 500 nanometers. Smaller screen and different milling disk. Here you can see actually 2 production scale Dispermats TM, and they are really cool. And what they are is basically a combination system, disperser slash basket mill all in one. The cowl's blade or the impeller blade is behind the gentleman with the gray sweater leaning against the blue drum. So they're not installed yet. But basically what happens is we first pre-disperse with the blade. That always stays on there, so don't take that off. And then when you're ready to do milling, you don't have to move the containers around. You just push a button on the control panel. The basket comes down and then you're milling. So on the left side, you can see the mill as it's in its upright position, as when you're adding the materials and so on. On the right side, this is the exact same machine, except this would be in the milling phase. Obviously, we are installing it, so that's how it gets shipped. It's not raised up, but when we're milling, we actually lower everything, and then that would be in the container. The basket would actually come down even further, down to the cowl's blade, and that's how we are milling. So this is a beautiful concept. One machine for production for both dispersing, mixing, milling, rather than having multiple pieces of machinery. So that's a really, really nice design. Then we have the APS, as I mentioned earlier, it's a vertical bead mill design, very nice, but really good only for lab scale. So here is you have 2 containers, you have a top and the bottom container. The top container will have your mill base. We pre-disperse first. When we're ready to do milling, we just swap out the milling, the impeller blade with a milling disc. We would add our beads, and then we close it up. You know, we can slide down the cover. There's a clamping ring that goes around it, and then we are milling. When we are ready to do to remove our mill base, we have a drain plug on the bottom of our container, and then we remove the drain plug. We hook up an air hose into that socket in the cover. There's a socket, and then we actually purge our mill base out of the container with air. And that's a very easy and efficient way of milling and also removing the product from the container. We can go up to about 7 liters, which is roughly 2 gallons of material. But going larger is not really sustainable because of the bead volume. You can have 100% bead loading. That means if I have, let's say, 500 milliliter of product, half a liter of product, I can also add half a liter of beads. So imagine if you have, 100 gallons or even more in production, you need 100 gallons of beads. That'd be very heavy and also extremely expensive and very difficult to handle from a cleaning perspective. So this is excellent for the lab, giving a really good milling performance, but not really scalable to production. Another slide on the APS, but people love it. When they clean it, then once all your product is removed, you just put the drain plug back in place, fill up the top container with a cleaning agent, and then you just close it up again and run it for a few minutes and purge it out, and then rinse and repeat until it's basically clean. Whatever comes out looks clean, and then that's a very easy and nice way of cleaning the APS. That's one of the advantages, and also with the air purge, it really helps, especially if you have thicker material. So then we have the horizontal bead mill. So our laboratory scale, it's called the SL mill, and then we go all the way up to production scale. There's always a need for a horizontal bead mill, especially if you go down to super small particles, right? So anything smaller than 500 nanometers, we really need to move over to a horizontal media mill. And then you can either do in circulation mode. That means if you look at that picture on the left on our lab unit, so we have obviously the supply vessel. There is an agitator and the pumping system that sits above it. that would then actually not really disperse, but kind of move the product around so it doesn't settle when it's in the container, and then pump it into our milling chamber. That horizontal piece right there, that's actually that's our milling chamber, and that's where we have also the rotor, and our beads would be in here. And then we would actually mill the material, and it would come to the front of the mill, and then it gets basically pumped back into the reservoir. So that's called a circulation mode. So depending on how small I want to go, I can circulate the mill base for a long time to go from, let's say, 1 micron all the way down to 100 nanometers. I may have to swap out the beads in the process to make the beads also smaller, but that will be the way that this mill functions, and the same concept on production scale. You can read this, so depending on the size, obviously, can go up to 6,000 RPM. Again, our milling speed is 10 to 16 meters per second. On our system, we can independently control the rotor speed and the pump speed. So that's really nice. We also have an air purging system. When you're finished milling, we can purge all the mill base out by air, which is an extra feature that really helps to maintain good cleanliness and quick removal of the mill base out of the mill. And then we have a nano kit available for super small particle size requirements, where we can actually use media all the way down to 0.1 millimeters. So that's super small, allowing us to really go down to very small particle size. And then different linings. Of course, we talked about the importance of ceramic versus metal. But it also depends on cost, right? And then we have different quality control options, especially when you're upscaling. That might be important, you know. This is the C control panel you're looking at here. We can see the speed on top. We can also look at the amount of energy you're putting in watts. That's the second window. And then we have, not window, right below the RPM with the red dot. We in the second row, we have the energy input in watts. Then we have the 4.1 Newton meters of torque. We would also have the actual tip speed displayed, which is really nice. You don't have to calculate it. Then the temperature, very important to always know, hey, how hot is it getting? What's happening? Am I cooling sufficiently? So that's very, very important, is to always have temperature readout on your panel, especially when you're milling, and then a temperature function. We can program cutoff values, ensuring safety. That means ADC, for example, can go higher, but that would be the max in this case. Then I could basically program the machine to stop once it reaches 80, or run at a different speed. On the new machines, we also give you warning stages, intermediate warnings. So we can program that, let's say at 70 C, a warning, and at 75, and then at 80 C, it would do whatever you want it to do. We can give products a name or a batch number, and then we can also program the important parameters into our batch. For example, the amount of energy we want to put in, or the RPMs, what diameter milling disc or blade diameter we had, what type of container, the size. H1, H2 is basically our safety threshold. So we have an upper and a lower limit in our container, especially when we're dispersing, where we don't want the blade to get lifted above the container while the machine is running. So we can set that there. And then obviously the cutoff values for our temperature, but I can also have cutoff values for speed or energy, depending on how I run my experiments. And then I can do net power calibration, which is really important, especially for upscaling. As the machines run without any product, they're already using energy, right, to turn the shaft and to operate itself. By doing a net power calibration, I can set all these values to an absolute 0 point. Now, making sure that then the values that I'm seeing on the display are related to my product and not any of the machine input. So the higher model can do it. Then we have the applications lab in Germany. Just a quick slide here. You can see a beautiful lab space. So if you're ever over there, we would gladly have you there and, you know, show you around or even run product for your German colleagues. And then our Wallingford lab looks a lot better than what you see is one of our first pictures, but we have a nice video on our YouTube channel. And we got really all the same capabilities as they have in Germany. But the big difference is we also have the beautiful lab support from the additives division from BYK USA. And that really sets us apart to our competitors, is that we don't want to just come in and sell you a hardware solution, a system with a dissolver or a mill. We want to really make sure that everything works properly, and that if there is ever any issues down the road where you have problems with, a formula it doesn't mill correctly, you have foaming issues or dispersing issues or reagglomeration, that we bring in our additive colleagues, and then they can give us exact, advice and recommendations on how to fix a problem and make sure that you will have good performance, not only with the equipment, but also with the overall formulation package, that you can rely on us at BYK to make sure that we give you full turnkey support, not somebody who sells you a mill and then leaves it up to you to operate it. And, if you have a problem, you're on your own. We really want to make sure that we do it differently and be a full solution provider. And please, if you have a project or anything you want, in the market to look at equipment, we'll gladly have you up and run your material with you and show you the differences between the basket mill and the horizontal mill or the APS. Or if you want to learn more about the dispersing milling process, please come up and let us know, and we'll make time for you. We will not even charge you for that. So with that, thank you. A lot to cover today. Took a little bit longer, but I hope that there was valuable information for everybody.
Yeah, very good, Andy. Thank you so much for sharing your expertise with us. We have a few minutes for questions. If anyone has any questions, just drop them in the chat, and we'll get to them. Or if we run out of time, we'll follow up directly with you. Also note, immediately concluding this, you'll get an automated link to this recording. Check it out, share it with colleagues. If you think of a question later today, next week, next month, you can simply hit reply to any of those marketing messages. They'll come to my team, and we'll funnel them to Andy and, or someone on his team or someone in your region. Andy, it always just blows me away of just the flexibility that someone can start, with the Disper mat, whatever model it is, and then grow as their needs grow, as their production grows. All of that, flexibility is just, amazing.
I think it's important, I mean, customers, obviously, money is always important, available in limited amounts. Budgets are tight, and I think having the ability to buy one machine and then accessorize it as you need it, especially not only for lab but production. Like, we have customers that buy they need a disperser, but they also need a mill and for manufacturing. And then they're like, okay, I buy a disper mat, dissolver, but then we also offer the milling, attachments, the basket mill attachments to the same disperser. So even in manufacturing, if somebody has many different color families, for example, they can just buy different baskets and dedicate them to different color families, allowing them, to basically just swap out a basket instead of having downtime on the machine for hours cleaning. So all you do is, okay, I have one basket for my blacks, one basket for my whites, and one for my, my greens or yellows. And then you just swap out the baskets, you do a quick flush, and then you move on. And they're not always taking the mills apart. We see customers that have other systems, they spend a lot of time cleaning. Our philosophy is we want you to actually work with the machines and not have so much downtime. So I think that is a huge advantage, going with the Dispermat solution.
Yeah, that's great. The cleaning portion of it is huge. And, while we have a few minutes left too, I was talking to Jonathan on your team the other day, and he was talking about, just a bunch of customers that have been using 3-roll mills, and based on, doing trials on the Dispermat, they've saved like an enormous amount of time. Can you elaborate or touch on that a little bit?
Yeah, I mentioned that in the presentation, but basically that is true. I mean, we had numerous customers actually just last year, I think 3 or 4, that came to us that were using 3-roll mills, and they were just getting exasperated by the amount of time it took to, get product, particle size reduced with the 3-roll mill. And don't get me wrong, the 3-roll mill is not a bad machine. It's just, if in some cases you may need it, if you have really, really viscous material, it's sometimes, easier to work with the 3-roll mill. But if you have, flowable viscosities where the material flows, there is much better solutions. And the 3-roll mill just take a lot of time. I mean, they're dangerous, one thing. They're not very safe. And then also, the basket mill will just blow it away from a performance standpoint. I mean, I said, we had one customer, they took 2 days to mill one material. And then with the basket mill, they came in and we were done in 1 hour and 45 minutes. They couldn't believe it. I mean, they thought that there was something wrong with our particle size analyzer, but we proved that was not the case. So it's pretty crazy. Hello? I'm not sure what happened, if you can still hear me, if John dropped off.
Am I back now?
I think, yeah, I can hear you.
Okay, that's good. I don't know, technical issues, gotta love them. But just to reiterate, if you have any questions or comments, you're always invited to the Wallingford lab to run trials. A huge benefit is just having our sister company, the chemists over there, if there are any questions, regarding materials, additives, things like that. So it's just a wealth of knowledge. Andy, any final thoughts before we wrap this up here?
I mean, not really. Just maybe you want to share the link to our YouTube channel and where they can find the presentation.
Yes.
That's always very important. They may want to share it with the other team members.
Yep.
And then please reach out if you have questions or you want to talk more in detail about your lab or even production needs. And we'll be more than happy to do an in-depth analysis with you, with your application, and maybe help you, make a good decision on if you need to acquire equipment.
Yeah, and we do have one question that just made it in here. So we'll go for that. What's the optimum volume / quantity of beads for the basket mill?
That depends on the size of the basket. For example, on a TML1, I think we use 40 millimeter beads. So it depends, there's not, but in the manuals, it always spells it out exactly, the bead volume. So it depends on the manufacturer of the basket mill, but for sure, the least amount of beads you would use in a basket mill. Okay.
Perfect.
Then you would go horizontal, and then obviously with the APS, you can do 100% bead loading. So, but really, the amount of beads is insignificant, and also the cost of the beads. We get that question a lot. I mean, it's really not an issue. So
wonderful.
And they last for a very long time. So beads are not a problem.
All right. And Andy mentioned the YouTube channel. Look in the chat. The link is there. That's where we have, the recording of this will be held there, as well as our previous webinars. So lots of good stuff there. There's also a quick video of the lab in Wallingford, so you can take a look there. And as always, reach out if you have any questions or if we can help in any way at all with your application. So Andy, thank you so much for sharing your expertise. I think we're doing this again in another month or so on I think innovations in production dispersing. So out there, you'll get the invite to that webinar if you're interested, or if you want to hear last year's. Again, hit the YouTube channel. So it's there. So thank you, Andy. Appreciate it, sir.
Thanks, everybody. I see, we had a good number of people today, and I really appreciate everybody that came on and reach out. Befriend me on LinkedIn. If you have questions, you can reach me out there as well, or just an email, to John, and they'll forward everything to me. But I'm on LinkedIn as well. I'll be glad to correspond with you there also. So thanks again, and have a good day.